Let us look at proposition number 10 of book 4 of Euclid's Elements. It's a beautiful construction. We have to create an isosceles triangle whose equal angles are twice the third angle. So let me show you what I mean by that. Let's say we have AB and then we need these angles to be 72, 72, 36. So look at this. These are isosceles triangle. The equal angles are these. And these equal angles are twice the third angle. So this is what we have to construct. I've basically hidden all the construction related steps. So that is why I'm able to show this. So let's remove this. So basically we start off with a line segment. It doesn't matter, how big it is or how small it is. We can start with any line segment. Now, the thing is, we have to cut this in such a way that AB by BC, let's say this point where we cut is C, AB by BC is equal to AC square. That is how we have to cut it. And in one of our previous propositions, we have done this. So let's take it step by step. Perpendicular at A, perpendicular to AB. Let's build the square on AB. ABDC as a square. So let's join these. And now what we'll do next is take the midpoint of AC. We will bisect AC. So we get E. And now keeping E as the center and BE as the radius, we draw a circle. So this circle, okay, let me hide off this circle. So this circle is at E and the radius is BE. And this circle cuts this line at this point. So let's mark that as F. And now on AF, we are going to build a square. Okay, now perpendicular to AF, we draw a line. We draw a circle of radius AF so that we can cut this line equal to AF. So let's mark that point as G. Then at G, we draw a line perpendicular to that line. And we mark this point as C. So this is the point where we have to cut AB so that AB by BC is equal to AC square. So basically we needed that point C. Let's draw a circle at A of radius AB. Now basically from B, again we have to cut this line AB such that that B and that point, the distance is equal to AC. So again, we have seen how to do that. At B, we draw a circle of radius AC and we mark this point of intersection of these two circles, D, and we join these points, B and D, A and D, and C and D. We don't really now require CD also. We have got the triangle that is required. This is 72 degree, 72 degree, and this is 36. Now we have to prove that this angle is twice this angle. This angle is equal to this angle, and it is twice this angle. Let's see. Let's take it step by step. Now, remember, we have constructed or we have identified C based on AB by BC equal to AC square. If you remember, we constructed a circle with center B and AC as the radius. So this from here to here it is AC. But that circle also cuts at D. So that means BD is equal to AC. BD is equal to AC, which means AB by BC, instead of saying equal to AC square, we can also say equal to BD square, because BD is equal to AC. And we can say that BD touches the circle P. Now, how can we say that? Because B is outside this circle P, and two lines from B, one cuts the circle and the other falls on the circle in such a way that AB by BC is equal to BD square. And again, we have seen if that is the case, then BD touches the circle. Angle BDC is equal to angle DAC. How can we say that? Because again, remember, BD touches the circle at a point of contact of a line segment CD, which cuts the circle. So this angle becomes an angle of the alternate segment, and they are equal. Again, we have seen this and proved it. So these two angles are equal to each other. Let's add angle CDA to both of them. To this, if we add CDA, what do we get? We get BDA. So we are adding CDA to BDC. Now, it's an equality, right? So we have to add it to this side as well. So let's add CDA to DAC. So our equality becomes angle BDA is equal to angle DAC plus angle CDA. If you look at angle DCB, this one is again equal to angle CDA plus angle DAC. Why? Because this is an exterior angle to this triangle, and an exterior angle is equal to the sum of the interior opposite angles. So which means angle BDA is equal to angle DCB. Angle DBA is equal to BCD. Since AB is equal to AD, angle DBA is equal to angle BDA. So which means what? Which means, let's bring in that also. So these three angles are equal to each other. Be very clear why we are saying that these are equal. Because AB is equal to AD, because they are the radii of the same circle, and AB, which means angles opposite to equal sides are equal. So this angle is equal to this angle is equal to this angle, we have already seen. Okay, so these three angles are equal. BD is equal to CD. How can we say that? Because these two angles are equal. So again, sides opposite to equal angles are equal. Again, listen carefully. BD is equal to AC, right? BD is equal to DC, right? That means what? AC is equal to CD, and angles opposite to these two sides, equal sides, will be equal. That means angle DAC is equal to angle CDA. So these two angles are also equal. Okay, if these two angles are equal, we can say, because we are interested in this angle, we can say angle DAC plus angle CDA is equal to 2 times this angle, 2 times angle DAC. Now we have already seen that BCD is equal to BDA, which is equal to DBA. That means angle BDA is equal to 2 times DAC, and similarly angle BDA is also equal to 2 times DAC. So we have not only constructed an isosceles triangle whose equal angles are twice the third angle in the triangle. Not only that, we have also proved it. Remember, I told you that it doesn't matter what the size of the line segment that you start off with. Where A is, it doesn't matter. Where B is, it doesn't matter. You will end up with the required triangle. So that was proposition number 10 of book 4 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it and refer to it. And if you think somebody else can benefit from it, please do share it. That's it for now. Bye.